So, good evening, everyone. I welcome you all to the problem solving session number 5 for the course Biointerface Engineering. This live session will be dedicated towards solving questions that are related to the week 5 assignment. So, the course Biointerface Engineering, this is being taught by Dr. Lalit Mohan Pandey. He is the Associate Professor in the Department of Biosciences and Bioengineering, IIT Guwahati, and I myself am a NPTEL PMRF TA. I'm Shilpa Nandi. I'm a PMRF in the Center for the Environment, IIT Guwahati itself. So I think a very less students have joined, so I'll wait one more minute. Till then, we can just go through the next slide. So this is basically a doubts and interaction session which is held every week. That is, weekly live session is conducted from 7 p.m. to 9 p.m. That is every Tuesday. So if you have any queries throughout the session, you can raise your hand, unmute yourself, and then raise the query. Or otherwise, the questions can also be posted in the chat box. Apart from this, we have a discussion forum for the course. So any questions related to the live sessions conducted can be raised there, or even any questions you have related to the lecture or any concepts you are not been able to understand, you can obviously post your question there. So these questions will either be addressed in the forum or in that period itself, or even in the next week's live session also. So for this week's session, we are going to have this kind of outline for this particular live session. So firstly, we will discuss most of the week 5 course content recap, as we are now, I think, lagging behind 1 week of the course. And basically we will be covering lecture number 13, that is aggregation of protein, then lecture number 14, kinetics of protein aggregation, and as well as lecture number 15, which is basically effect of surfaces on the aggregation of protein. So these three particular lectures that was being taught in week 5, we'll go through a recap of this, and then later on in the session we will also try to solve various assignment questions related to that particular week, week 5, which is already uploaded in the portal. Fine. So we will move on with the lecture number 13, which is aggregation of protein, and we'll see what all was taught in there. I hope everything is quite visible properly and you are able to listen to me as well. Okay, fine, we'll move ahead. So we will go through a quick revision of this content. Basically, in lecture number 13, we started with how protein aggregates. So in the previous week, we went through what are the basics of protein. So basically, any misfolded protein adopt a conformation that causes its polymerization into aggregates and organized fibrils. So basically, there are four major uh, forms of protein. First, it is a native one. Then it undergoes unfolding and it possesses an unfolded structure, unfolded form of protein. Then later on, it basically aggregates and forms an oligomer, and later on in the last stage, it forms an aggregate. So these four stages, that is native, unfolded, oligomer, and aggregate, are the basis for the for the transformation from a native protein to an aggregate one. So what are the effects of protein aggregation basically? So this protein can become inactive when the native conformation is perturbed. Basically, when this native conformation changes to any other conformation, that is either the unfolded one or the oligomer or even the aggregate, it becomes inactive. Right, basically it loses its functionality. And apart from this, this could lead to several conformational diseases. So when protein undergoes a misfolding, it leads to fibrillar structures that deposits in the tissue, and these aggregates basically are associated with various neurodegenerative diseases including Parkinson's, then Alzheimer's, also Creutzfeldt-Jacobson disease. So various other prion diseases comes under these kind of conformational diseases. So any kind of protein aggregation can lead to various diseases as well. Next, we went through the characterization of protein aggregation. So what are the various assays and analysis that is used for characterizing a protein aggregate? So first one is thioflavin T fluorescence assay. Then there is analysis of residual protein. Third one is determination of hydrodynamic diameter. Fourth is analysis of secondary structure, and lastly it is morphological analysis. So we'll start from the first one, that is thioflavin T fluorescence assay. So thioflavin T is basically a dye that binds to the fibrils with its long axis parallel to that of the fibrils, right? So there is an excitation or emission that ranges from 450 to 482 nanometer, wherein you can read the aggregate or protein aggregate data. And other dyes that are being used in this are Congo red, then ANS dye as well. Then we'll also discuss the determination of hydrodynamic diameter. So this is basically an assay. This is basically determined by using an instrument called dynamic light scattering, that is DLS, in which a laser beam is basically and passed through the sample, and the fluctuation of the scattered light are then detected. So this particular instrument is based on Stokes-Einstein equation, which is particularly given as dH is equal to kBT divided by 3 pi eta d. So in this, dH is the particle size and kb is the Boltzmann constant, T is the absolute temperature in Kelvin, eta is your viscosity, and D is the diffusion coefficient. So basically we are going to assess this diffusion coefficient, and the relation is done with the particle size of the protein sample, that is the dH. So next, in this particular lecture, it was also being taught about the intermolecular forces that are the basis for protein aggregation, or which are involved in protein aggregation. So first one is your dispersion forces, that is London van der Waals forces. Second is electric double layer, and third is short range forces, which includes various hydrophobic bonding as well as hydrogen bonding, ion pairing as well as dipole interactions. Now we already studied this dispersion forces, as well as we already discussed this dispersion forces and short range forces, but this electric double layer term is new for you. Okay, so what is this electric double layer? So as you can see, in a stable solution or any colloid, the counter ions and coions are non-uniformly distributed, which forms an electric double layer. From the figure you can see that in any stable solution or colloid, the counter ions or the coions are like positive ions and the negative ions are non-uniformly distributed, and which leads to the formation of an electric double layer. So some of these counter ions are surface bound. So whatever ions are surface bound, they are known as, they actually in a group, they are involved in Stern or Helmholtz layer. So this is particularly known as Stern or Helmholtz layer. Whereas some counter ions are diffused around the atmospheres near the surface. So these particular ions are known as diffused electric double layer. So in the figure you can see the co-ions that are present at the surface, and this form the Stern layer, whereas uh, any other counter ions that are diffused around the atmosphere, so they are particularly the forming the diffused electric double layer. So I may just show you from here. Let me. So this is basically the Stern layer forming, and these are the counter ion in the atmosphere. Right. Can you just now see in the figure which is representing the Stern layer and which one is the diffused counter ion in the atmosphere that forms the diffused electric double layer? Okay. Uh, we can go through the next slide. So after electric double layer, we also went through what is this T by length. T by length is represented by 1 by K. So basically, this is the distance from the surface into the solution up to the point where the effect of the surface is felt by the ions. That is the dk length. So from the figure that is present at the bottom, you can see that it is the distance from the surface to the point where the effect of the surface is felt by the ions. So this particular distance or this particular length is the d by length, that is 1 by k. Okay, so don't confuse between k and 1 by k. So this d by length depends on the properties of solution and not on the surface property. Right. So you have to also remember this particular thing, that d by length is dependent on the properties of the solution and not on the properties of the surface. So K is particularly here given as under root summation of rho multiplied by Z E to the whole square divided by epsilon naught epsilon K T, and the unit here is per meter. So when you convert this in 1 by K, your unit will again become into meter, right? So the d by length for particular electrolytes in several ratio is also given, like for 1 is to 1 electrolytes, for 2 is to 1, 1 is to 1 electrolytes, and for 2 is to 2 electrolytes as well. So next we'll move to the lecture number 14, that is kinetics of protein aggregation. So in this particular lecture, firstly we went through what are the various protein aggregation pathways. So we have particularly four pathways by which a protein aggregates. So first one is through unfolding intermediates or unfolded states. So the number 1 you can see, it converts from a native protein to an intermediate protein. In the figure you can see that N converts to I, and this is probably a reversible one, and 1 is being given there. So this 1 is the first pathway, that is through unfolding intermediate and or unfolded state. Now next is 2A. In the figure you can see 2A, that this pathway is basically through protein self association, or you can say the colloidal interactions, particularly in native state. So the native state can convert into the aggregate form, self association, that is the colloidal interaction, N to A, or even it can be A to U, unfolded to A. Next is 2B, which is upon chemical degradation or directly linking the protein monomers. So through chemical degradation, this 2B, that is N to A forms, right? Native structure to aggregate structure, 2B. And lastly, the third 3 here in the figure you can see it represents that the uh, native structure transforms into the D1 state. So D is basically the degraded chemically. You can already read it. So upon chemical degradation, indirectly changing the aggregation tendency of the protein. And also in the pathways, you can see that the aggregate later on converts into a precipitate. So this is, as you can see, the arrow is on a single side. So it is basically a non-reversible one. Fine. So these are the basically four pathways by which the protein aggregates. So we will move on to next is the aggregation process in bulk. So how does a protein aggregates in bulk? So various external factors that leads to the external factors as in pH, temperature, ionic strength, solubility, shear may be any kind of mechanical shear, physical stress, and lastly it's adsorption or the surface adsorption. So adsorption occurs in case of surface, but here aggregation process is occurring in bulk. So apart from adsorption, other external factors are being responsible here. So various external factors lead to the conversion from native to conformation to the D state. So what was this D state? D was actually the degraded stage, right? Then after these conformational changes, there is a formation of nuclei. So this formation of nuclei is also referred to as nucleation, right? Like formation of aggregates is known as aggregation. So formation of nuclei is also known as nucleation. So all these three events like the conformational change due to external factors, then the unfolding or the nucleation process, these all are constituted in the lag phase. So basically lag time or lag phase, as you can see from the figure, these particular events occur in this lag phase. And lastly, after lag phase, we have the growth phase, and after growth phase, we have the stationary one, right? So after formation of nuclei, there is a formation of aggregates. These aggregates, or you can say these, they form a fibrillar structure at the bulk. So when N converts to D, there is a K1, that is the rate of formation of the degraded structure. Then there is a K2, that is the rate of aggregation, and as you can see during the conformational changes, K2 is much higher than K minus 1. So K minus 1 is the conversion back from the degraded stage to native stage. So all molecules in D state will convert into A state only when K2 is much higher than K minus 1, right? And again, when K1 is much higher than K2, then only uh, then only the concentration of molecules in the D state will increase, right? So we also went through these factors again affecting the aggregation, that is the pH. Changing a pH can cause aggregation, changing the temperature, changing the ionic strength or solubility as well as shear. We can see that the protein can lead to aggregation. So next, in the kinetics of protein aggregation lecture, this aggregation kinetics in bulk was being studied, wherein minus dn by dt is equal to kn square. So this, when if you integrate it, like if you take the n as n naught or the initial number of molecules, and nt is the number of molecules at that particular time, you will get this particular expression, that is nt is equal to n naught by 1 plus n naught kt. So the half time of aggregation based on this particular expression can be also derived, that is T half is equal to 1 by Kn naught. So we can try to solve this. Let me see if I think this was also discussed in the lecture, but we can try once. so that you may also recall what what exactly these expressions, or from where exactly these expressions are coming from. So you can figure out from the figure present just on the left, that one molecule plus another molecule leads to a combined molecule. So again, that combined molecule attaches with another particular molecule to form the next, and so on. So this particular process occurs again and again until a proper aggregate is formed. So if you can see, I'll ink. Okay, okay. So we will solve this one. So this is basically what aggregation kinetics in bulk, right? So what happens is, one molecule plus another gives this particular, and this is our K1, and similarly it can be K12 if this goes on to create another. So pardon my diagram. And next, if we see, this follows a second order reaction basically, that is dN by dt is equal to Kn square. So this is a second order reaction. Again, if you take the initial n as n naught and the final as nt, and try to integrate it, so, and time as 0 to t, so we'll get something like this, right? So if you integrate this, you will get 1 by nt minus 1 by n naught is equal to kt. And now if you take this 1 by nt on one side and kt on the side, so this will become 1 plus n naught, right? So later on, if you inverse it, like reciprocate it, it will be something like this. And now you can see what's the value for nt, which is n naught by 1 plus n naught kt. I think this was the formula, that is, yes. So nt is equal to n naught by 1 plus n naught kt. Also, if you take out the t half, so how can we derive the t half? Okay, so how can you derive the t half here is, so n naught, sorry, pen was not working. So n naught by 2 1 plus n naught kt by half. So t half will become 1 by kn naught. So this is 1, right? So I hope you got this one. Okay. So we were discussing about this particular aggregation kinetics in bulk. So the role of diffusion constant, also the rate of aggregation K is given as 8 pi dA, and D is the diffusion coefficient and A is the area for different spheres. K is equal to 4 pi D1 plus D2 and A1 plus A2. So this particular Stokes-Einstein equation, as we already said, that DLS, that is dynamic light scattering, is based on Stokes-Einstein equation. D is equal to kBt by 6 pi n eta A, wherein you can find again the K, and K is inversely proportional to the eta, that is the viscosity. Right, so the A is the radius of the sphere, eta is the viscosity, and D is the diffusion constant. Okay, we will move ahead now. Uh, After the aggregation process on bulk, we in the same lecture, in the lecture 14, it was also discussed about the aggregation protein on surface. So external factors here is basically the adsorption, that is adsorption on surface, which leads to the conformational changes, that is the end on and side on adsorption, and then it again we have the nucleation similar to that in case of bulk, and lastly we have the formation of aggregates, that is aggregation, that is fibrils are present at the surface. So again in this case also during the lag time we have this particular processes or events, that is adsorption, conformational changes and nucleation, whereas aggregation process does not occur during the lag time. Right. Also, one more thing that is needed to be noted is in case of hydrophobic surfaces, it favors the adsorption of proteins, whereas in case of hydrophilic surfaces, this results in very little protein adsorption. So you must also remember this particular case. Questions may be asked depending on this thing as well. So next, similar to that of the rate of aggregation in case of bulk, there is a determination of rate of aggregation in case of surface as well. So this is basic. This particular determination of rate of aggregation is based on the sigmoidal model of Boltzmann equation, which is given as IT is equal to I max plus I max minus I naught divided by 1 plus e to the power t naught minus t by tau. Herein 1 by tau is the apparent rate constant, that is the k. So k is the uh, rate that we are looking for, and lag time is estimated as t naught minus 2 tau. So if you again try to solve this one, or this will again lead to a derivation, that is it is equal to I max 1 minus e to the power minus kt. So a linear slope, that is when you plot a graph between the THT intensity versus the time, a sigmoidal shape graph will be formed in which the lag time, uh, the lower, as you can see from time 0 to around time 3 hours, it is the lag phase in which you have adsorption, conformational changes as well as nucleation. Then we have the growth rate, and lastly we have the stationary phase, right? So during this growth rate, you through a linear slope you can find you can get this equation, that is it is equal to kt plus c, and henceforward you can also know whatever the values of k as well as t is. Okay, next we went through the we have in lecture 15, like that is the effect of surfaces on aggregation of proteins. So what we studied here are various factors that affects the aggregation process on surface. So what kind of factors are surface roughness, then we have surface wettability, surface chemistry as well as surface potential. So we will see what is the effect of the surface roughness on the protein aggregation as well as the surface wettability as well. So from the next figure, as you can see, in case of modified surfaces, that is if there is a clean glass, so it is highly hydrophilic in nature. And if we have an amine modified surfaces, so we have a hydrophilic, but the contact angle here is 62 degree. And next we have octile modified surface, which is hydrophobic in nature. So when your contact angle is greater than 90 degree, we term it as hydrophobic, and when the contact angle is less than 90 degrees, we term it as hydrophilic in nature, right? So in case of this octile modified surface, we have the theta as 102 degrees. And in case of mixed surfaces basically it will have both the amine modified as well as octile modified surface. This will have a moderate hydrophobic nature, that is between 62 to 102 degrees. So these modified surfaces are also known as SAMs, right? You might have heard during the lecture. What is this SAMs? SAM is self-assembled monolayers. Okay, SAM is self-assembled monolayers. So we'll see what is the effect of these wettability of surfaces with mono and mixed SAMs. So you can see if we plot a graph between the contact angle theta and the fraction of amine, that is Fa. So you can see there is a linear slope. So and just below that we have this Kc equation, that is cos theta is equal to Fa cos theta A plus F naught cos theta naught. So F naught is Fo, sorry, it's not F naught, it's Fo. So O represents here the octile modified surfaces, and A represents here the amine modified surfaces. So Fa is basically the fraction of amine modified surfaces, and Fo is basically the fraction of octile modified surfaces. So when your contact angle is 100 degree, so the fraction of amine is the least one, right? That is 0. And when your fraction of amine is around 1, so we have the contact angle would be something like 61 or 62, which we already saw, right? When you're in the previous slide, you see here it's already written. In case of amine modified surfaces, it is theta is equal to 62 degrees, right? So similarly you can plot these kind of graphs and know how does wettability of surface affects the protein aggregation, right? So similarly we already studied this kinetics of aggregation, that is lag time. Then there is growth rate, which can be taken out from the growth phase or the exponential phase, as you can see. And lastly it's the stationary phase. So next we'll move on and again see again. So this is a real-time graph based on that TST intensity versus time. So four different self-assembled monolayers or modified layers. So first one is amine SAM. Second, green depicts here the amine SAM. So the purple one is mixed or 1:1 SAM, red is the octile SAM, and lastly the you can say it as the violet one is the mixed beads, right? So you can see which of the following has the highest lag time. So when you highest and the lowest lag time from the first figure or the first graph. So the red one, that is the octile SAM, has the maximum duration of lag time, right? So in the right you have a table in which you can see octile has around lag time of 14, and in case of what, which has the lowest one, it is the mixed 1:1 beads. So blue one represents blue, or you can see the violet one representing the mixed beads, have the lowest lag time, right? So this particular lag time you can assess through this graph, and further we can also determine the rate of aggregation through this particular graph itself. Like if you plot a growth curve and if you take out the linear slope, you can determine the rate of aggregation. Also, if how will you access the protein aggregation, or you will know whether your protein has been aggregated or not? So you can perform FTIR, or to see whether what are the changes in the secondary structure of protein. Also, you can perform AFM, that is atomic force microscopy. Through atomic force microscopy, we can see the surface morphology after aggregation and as well as before aggregation. So you may just uh, analyze both before and after aggregation pictures and look for the changes or the surface morphology changes after aggregation, and basically compare both of them. So in case of FTI, we already discussed in the like last session as well. FTI is basically Fourier transform infrared spectroscopy. So secondary structure involving alpha helix, beta sheets, and loops and turns. You can just determine it from the peaks, what are peaks of the graph that you get from FTI. Also, changes in surface roughness is given by Ra is equal to 1 by n summation of Zi, that is I is equal to 1 to n. So Zi is the height of the particle. Um, So in the next figure, we have given few of the SAM groups, that is self-assembled monolayers group, before adsorption and after adsorption RA values. So RA, you can see that before and after there is a huge change. For example, if you take that of amine 1, so before adsorption it is 0.63 and after adsorption it is around 3.72. So aggregation has happened, or then only after adsorption the RA has increased. So next we'll move on what was being again taught in this lecture 15. So it was, we also saw the relation between the surface roughness and adsorbed mass. So basically what happens when adsorbed mass increases, how does it increases? If there is an increase in surface roughness, it will automatically increase. Also, protein adsorption triggers the conformational changes and drives the aggregation. So in the graph, you can see we have plotted adsorbed mass versus the Ra values, that is the surface roughness values. So as the surface roughness increases, the adsorbed mass also increases. So highest surface roughness you will find in the mixed category SAMs, that is 1:1 ratio. So the adsorbed mass is also the highest in that category. Similarly, you can find out the relation between the surface roughness as well as adsorption rate by mt is equal to m naught x e to the power minus kt. So mt is the mass, adsorbed mass at time t, m naught is the initial mass absorbed, and e to the power minus kt is, k is the your rate of aggregation, and t is your that instance of time. So in here also you can see, if you plot a graph between adsorbed mass and time, you will find a sigmoidal kind of curve, and again through the growth phase, during the growth phase, from that linear slope, that is this particular expression is derived, that is mt is equal to m naught e to the power minus kt. Also in this we discussed how this hydrophilic or hydrophobic surfaces has the effect on the aggregation, right? So we already discussed this, what kind of surface favors your aggregation of proteins and what kind of surface does not favor. So if you have a native insulin, so a native insulin particularly has both the hydrophilic surface as well as a hydrophobic core. So in a particular surface which has a water layer, so water layer will be termed as highly hydrophilic surface. uh, so in this you can see the hydrophilic surface sits on the water layer. Similarly, when there is a hydrophilic SAM, that is self-assembled monolayers. So in this case there is hydrogen bonding that accelerates the aggregation between the insulin and the surface. Again, if you have mixed SAMs, so there will be both hydrophilic as well as hydrophobic interactions, and dual effect will be seen, that is hydrogen bonding will be also seen as well as hydrophobic interaction will be also observed. And lastly, in case of hydrophobic SAMs, there will be hydrophobic interaction that leads to the fibril formation, right? So lastly, in this particular lecture, that is lecture number 15, there we also went through various therapeutic solutions or the key approaches that helps to avoid the aggregation of protein or helps to avoid the misfolding of protein. To be very specific, misfolding of protein. So one of the key approaches is the inhibition of protein aggregation. Uh, Inhibition of protein aggregation as means with any kind of external factors you can inhibit the protein aggregation, that is the conversion from native to degraded and degraded to unfolded or the aggregated state. Next is interference with post-translation peptide changes before the misfolding or aggregation step, right? So before any misfolding or aggregation step, you can again go with interfering it with various post-translational peptide changes. So this won't allow the aggregation of proteins. And lastly, we have upregulation of molecular chaperones or aggregate clearance mechanism. So what is this upregulation of molecular chaperones? So molecular chaperones are basically uh, they basically help in conversion to the native state. So they basically converts the misfolded protein to the native state protein. So once the aggregate has been formed, you cannot interfere it with any other um, approaches, like you cannot inhibit the process with certain factors, or you cannot interfere it with post-translational peptide changes. So once the aggregate has been formed, there are basically two steps. One is either you can upregulate the molecular chaperone so that this misfolded aggregates can be again converted back to the native state, or you can go for various aggregate clearing mechanisms. So you can basically remove those aggregated proteins from the tissue itself, right? So this ends your lecture 15 recap as well. So probably we went through most of the topics that was being covered during the lectures. That is lecture number 13, lecture number 14, as well as lecture number 15. Apart from that, now we will try to solve certain questions specifically to that helps you to solve the questions of assignment number 5. So, so we have our first question here. So we'll take 1 minute break. Let me have some water, and then we will again start to discuss various questions, right? So you can see the first question that has been displayed in your screens. The first question is, which of the following disease or even diseases occurs due to aggregation of protein? Okay, so Amardeep is saying that the answer is D. Okay, so your options here are, we'll wait for another all the students so that they can also understand. Okay, we'll then discuss, and fine, your answer is totally correct. The answer is option number D. However, we will see how or why these are the diseases that particularly occurs due to the aggregation of protein. So first option is your Alzheimer, second is Parkinson's disease, C is Creutzfeldt-Jakob disease, and D is all of the above. So as Amardeep said, the answer is D, that is all of the above. So you're totally right about that. Yes. So why Alzheimer or Parkinson or Creutzfeldt-Jakob occurs, particularly this due to these misfolded or conformational changes in the protein. So you will see what is this Alzheimer's basically. So Alzheimer's disease has been identified as a protein misfolding disease, or you can call it as proteopathic or proteopathy, which occurs due to the accumulation of abnormally folded amyloid beta proteins, which is basically in the brain of AD patients. So in the brain, we have this amyloid beta protein that gets abnormally folded, or you can say misfolded, that leads to Alzheimer's. Next is the Parkinson's disease. So Parkinson's disease again, it is the second most common neurodegenerative disorder, which involves the misfolding of a protein that is named as alpha synuclein, or you can write it in the short form as alpha syn. So whose aggregation generates inclusions or inclusion bodies known as Levy bodies or LBs that can be found in the neurons. Again, this is also occurring in the brains of the Parkinson's disease patients. So lastly, we have this Creutzfeldt-Jakob disease. So it is also a rare fatal disease that is presenting with rapidly progressive neurological defects or deficits caused by the accumulation of misfolded form, that is PRPSC, that is prion protein or scrappy. SC is basically scrappy form of prion protein. So PRPSC is basically scrapy form of prion proteins of PRPC, right? So accumulation of misfolded form is the scrappy form and the native form is your PRPC. Uh, so in case of Creutzfeldt-Jakob disease, it is the accumulation of misfolded form, that is prion of, that is scrapy form of prion proteins. In case of Parkinson's disease, we have this misfolded protein named alpha synuclein, and in case of Alzheimer's, we have this abnormally folded amyloid beta proteins. So I hope now you know what are the exact protein names as well, not just that you know it from the lecture series, that various conformational diseases like Alzheimer, Parkinson, Creutzfeldt-Jakob, or even other prion proteins diseases coming are also come under this aggregation of protein disease category. So okay, the answer to the first question was all of the above. We will now move on to the second question. So our second question is, which of the following is a method or is methods for characterization of protein aggregation? So your options here are A, determination of hydrodynamic diameter, B, thioflavin T fluorescence assay, C is secondary structure analysis, and D is all of the above. So you have to basically answer that which of the following is a method for characterization of protein aggregation. Fine, you have got four options and one of which is correct. Also, like the previous question, the number one question, if you had any doubt regarding that also, you can again raise your hand or ask it here itself. So I'll try to cover few questions and I'll try to solve it like on the basis of on what's the basis of it, so that you may also remember it is very easily. Right, if we just go through very fastly through the questions and we don't follow up the concepts that are behind it, you may again face certain problems in answering the questions. So Amardeep says the answer is C, that is secondary structure analysis. Fine. Uh, so Amardeep, why not A and why not B? It is fine. If you don't know the answer, that's also fine. You won't get any punishment here. So, which of the following is a method or methods for characterization of protein aggregation? So, I think when I was going through lecture number 13 recap, during the first two slides only this particular topic arised. So, Amardeep says that the answer is C. So, we will look for what is the answer. So, the correct answer to this particular question is option number D, that is all of the above. So when I was going to lecture number 13, you can also go through the lecture number 13 from your NPTEL course or NPTEL portal. You will see they have discussed what are the various methods for characterizing the protein aggregates. So we had these particular five methods. So first one was thioflavin or THT fluorescence assay. Second is your analysis of residual protein. Third is determination of hydrodynamic diameter. Fourth one is your analysis of secondary structure. And lastly, your analysis of the morphology. So we already have all the three options here, that is determination of hydrodynamic diameter, then THT fluorescence assay, and the C is your secondary structure analysis. So the correct answer is all of the above. Now, I think I already discussed this hydrodynamic diameter determination as well as THT fluorescence assay. So the secondary structure analysis you can obviously do via FTIR. Uh, so I already told you that the protein aggregates can be studied using FTIR as well as morphological analysis. So I think I lost my connection in between. So we will go back again from the starting. That so for determination of hydrodynamic diameter, what do you use? Which kind of instrument do you use? I think this I uh, discussed during our recap of the week 5 assignment, week 5 course content. So for A option, that is the determination of hydrodynamic diameter, you basically use the instrument name DLS, that is dynamic light scattering, right? And THT fluorescence assay, you basically analyze the intensity. And secondary structure analysis involve instruments such as FTIR, right? Fourier transform infrared spectroscopy, that from where you can analyze the peak relating to alpha helices, beta shades, as well as various loops, as well as random coils. Apart from that, we have morphological analysis. How can you determine the morphology of the aggregated protein? Using which instrument do we analyze the morphology of the aggregated protein? Do you have any idea? So we discussed it during our lecture 15 recap, or I guess lecture 14 recap. So we have our AFM, that is atomic force microscopy, from which we can determine the change in the morphology of the protein, aggregated protein. Fine. So I think, is there any doubt in this particular question? So if not, we will move ahead. You have to basically remember what are the various methods or assays that are involved in characterizing a aggregated protein, right? How can you analyze a protein aggregate? Okay, we will move on to the next question, that is question number 3. So the relation between diffusion constant D and the particle size is given by A. Stokes-Einstein equation, B. Wenzel equation, C. Young Laplace equation, and D is your Casey equation. So during the recap, I think I already discussed about the Stokes-Einstein equation as well as the Casey equation. However, we did not went through these two options B and C, that is Wenzel equation and Young Laplace equation. So you have to tell me which of the following equation gives the relation between the diffusion constant D and the particle size. You have your options right in front of you. So this particular question, if you remember what was the expression for that particular equation, you may be able to give the answer. So your options here are Stokes-Einstein equation, Wenzel equation, Young Laplace equation, and Casey equation. So I have got the answer from Amardeep, that is, he's saying the answer is A. So what is particularly the Stokes-Einstein equation? If you can read out loud, can you? What was the expression for it? It's fine if you cannot, that's also fine. Okay, it's fine, no problem. Yes. So Amardeep, yes, you are absolutely correct in this case. So the correct answer to this question is option number A, that is Stokes-Einstein equation. So I during the recap we went through this particular equation and its expression. So we will see again what are the various equations pertaining to the question. So you must remember the equations and not just that particular answers equation, but also the other options. So I'll try here to make the concepts clear. So first, that is the Stokes-Einstein equation is given as dH is equal to kBt by 3 pi eta d. So kB is your Boltzmann constant, T is the absolute temperature in Kelvin, then 3 pi eta is your viscosity and D is your diffusion constant. So this particular equation, that is Stokes-Einstein equation, is the basis for DLS. DLS is your dynamic light scattering. Now again, where do we use this DLS? So in the last question, we have this determination of hydrodynamic diameter. So this hydrodynamic diameter is your dH here. In the Stokes-Einstein equation, this dH is basically your hydrodynamic diameter. So the determination of hydrodynamic diameter using the instrument DLS, that is dynamic light scattering, which has the basis as Stokes-Einstein equation. So the determination of hydrodynamic diameter is done for the characterization of protein aggregation. Again, if you relate back in the previous question, we saw that characterization of protein aggregation can be done by determination of hydrodynamic diameter. I think option A is quite now familiar. You guys might be now familiar with this Stokes-Einstein equation. Option B, that is Wenzel equation. So in our week 2 course content, in our week 3 course content, or if you go through the week 3 course content and you revise it, you will find this particular equation, Wenzel equation. So Wenzel equation is basically given by cos theta is equal to Rf cos theta naught. So in this wettability and Rf is your roughness factor. So how the surface roughness can determine the wettability. So it basically gives the relation between the wettability and the surface roughness. So surface roughness is given by here the RF, that is the roughness factor. Cos theta is the initial contact angle theta, and theta naught is your contact angle that is arising due to the increase or decrease in the roughness factor. So Wenzel equation basically gives the relation between wettability and the roughness factor. Option number C, your Young-Laplace equation. So again, this particular equation we studied in our week 3 course content. So which is given as del P is equal to P internal minus P external is equal to gamma 1 by R1 plus 1 by R2. So gamma is your interfacial tension, and R1 is the internal radius and R2 is your external radius. So Young-Laplace equation is basically the basis for pendant drop shape analysis. If you go back and see what are the various methods for determination of surface tension, you will see there is a particular method, that is pendant drop shape analysis, wherein we use this particular equation, which is Young-Laplace equation. Lastly, we have option number D, that is Casey equation. So Casey equation is given as cos theta is equal to f1 cos theta 1 plus f2 cos theta 2. So we already studied this particular equation in today's lecture. So Casey equation basically gives the relation between the roughness factor, the wettability, that is the contact angle, based on the chemical heterogeneity. So why I am telling here chemical heterogeneity? So you can see if I modify the surface with a particular amine or particular fraction of amine or particular octyl modified surface. So F1 can be regarded as Fa and F2 can be regarded as Fo. So A is your amine and Fo is your octyl. So F1 would be the fraction of amine modified surface and F2 will be, that is Fo will be the fraction of octyl modified surface. So hence we say that wettability can be also related with the chemical heterogeneity that is being found on a particular surface. So how we will find that particular contact angle, which is basically given by this Casey equation, cos theta is equal to f1 cos theta 1 plus f2 cos theta 2. So theta 1 and theta 2 again will, if you think it as theta 1, take it as like theta 1 can be taken as fa and theta 2 can be taken as fo. So in case of amine modified surface, it will be theta 1, and in case of octyl modified surface, the contact angle will be theta 2. This is just an example. Uh, it can be any other modified surface as well. So basically Casey equation, you have to remember wettability in terms of chemical heterogeneity is given by Casey equation. Okay, we will move on to the next question we have is question number 4, which is which of the following sequence represents the events of protein aggregation on solid surfaces? So you have 4 options. First option is conformational change, then we have adsorption, then we have desorption, and lastly aggregation. Option number B states nucleation, then conformational change, then adsorption, and lastly aggregation. Option number C is adsorption, conformational changes, nucleation, and aggregation. And lastly, first you have conformational change, then unfolding, then nucleation, and then aggregation. So you have to depict that which of the following sequences or the events sequences represents the events of protein aggregation on solid surfaces. So okay, we have the answer as option number C. Fine. We will see why not other options. We will wait for other people to absorb the question and try to correlate with it, and we will move ahead. So till now we already solved 3 of the questions. Uh, so I hope there is no doubt. Then only I'm moving forward. So if you have any doubt pertaining to that particular slide, you can just write it away here, or even you can just unmute yourself also and raise the query, right? So we will let everyone to absorb the questions and then we will see. So you are getting what's the question is, right? So what are the events of protein aggregation in case of solid surfaces? So how does the protein basically aggregates? Okay, so Amardeep said that the answer is C, which is firstly we have adsorption, then the protein undergoes conformational changes, then we have nucleation, and that is formation of nuclei, and lastly we have the formation of aggregates or fibrils at the surface. So Amardeep, you are correct. Your option number C is the correct answer to this particular question. Yes, also you must remember that in this question we have been asked the events for protein aggregation on solid surfaces. So if you are given any time the protein aggregation in case of bulk, that also you must remember. So how does a protein aggregation in case of bulk occurs? Okay, we will first see how does this protein aggregation in case of solid surface occurs. Then we will see how does protein aggregation in case of bulk occurs. Okay, so you are correct. So this is a particular sequence of events that occurs during the protein aggregation in case of solid surfaces. So firstly, we have adsorption. That is, it is basically a factor that leads to aggregation of protein. Then later on, there is a conformational change which may be unfolding, and then we have multilayer adsorption or formation of nuclei. So this formation of nuclei is also known as nucleation. And lastly, we have formation of aggregates or fibrils at the surface. That is known as aggregation. Right. So this was for solid surfaces. So can you tell me what will be changed here if we have protein aggregation in case of bulk surfaces? Can anyone tell me? Sorry, in case of bulk, if a protein aggregation occurs in bulk phenomenon, then what will be the change here? So in case of bulk, this will be this particular adsorption will be replaced by various external factors: pH, temperature, stress, or shear, you can say, or solubility change, or even ionic strength change. Can you see what am I writing? Yes, probably. So in case of bulk, this adsorption, yes. So in case of bulk, this particular adsorption will be replaced by various external factors. So you must remember if any time such questions arises, so you do not confuse between the protein aggregation events in case of a solid surfaces versus a protein aggregation events in case of bulk, right? I think any doubts you have in this question? If there is no doubt, we will probably move ahead. Okay, so your fifth question is, so till now whatever we are solving or whatever I will be probably solving in the other like in later on in this session are all the questions are taken from lecture number 13, 14 and 15. So it's a very direct questions. If you go through the lectures like once or twice, you will be able to answer it very fluently or very efficiently, right? So we have the fifth question, which is which among the following is the first step of protein aggregation? So right now we already went through what are the events or what are the sequences of protein aggregation, and herein we don't have that particular thing that first step of protein aggregation in case of surfaces or in case of bulk. So you have to just answer which of the following is the first step in case of any protein aggregation. So your options here are A is desorption, B is unfolding, C is nucleation, and D is none of the above. Answer C. Okay, so Amardeep is saying that nucleation is the correct answer. We will see. So can you recall back what you have to say what is the first step of protein aggregation? Just now we went through the figure in which we had the four events, that is first it was adsorption, then there is conformational changes, then there is formation of nuclei, and lastly we have formation of aggregates. So how can you just say that option C is correct? Do you know what is nucleation? So formation of nuclei is basically nucleation, and if you think back, just now we studied that nucleation is not the first step. It is basically your second step, right? It's not the first step. So what would be the first step? Sorry, nucleation is your third step, right? Okay, yes, I got the answer as B. Yes, now you're thinking, so you have to recall back and relate it to everything, whatever the sequences are there in in case of protein aggregation on surface, in case of protein aggregation of bulk, and then you have to give the answer. If you do such mistakes, again, your answer won't be correct, right? So yes, now as you gave the answer as B, so Amardeep, B is unfolding. Right. So yes, option number B is correct, which is your unfolding. So firstly, the native structure is unfolded. Unfolding occurs. Then there is the formation of oligomers, that is the formation of, there will be conformational changes when unfolding occurs, and then oligomers will form, basically formation of nuclei, and lastly we have the formation of aggregates. So don't get confused between nucleation and unfolding and desorption. And why not desorption? So desorption is not a step or not a particular event in protein aggregation, right? And none of the above is also not an exact option, not a correct answer. So now you got it how to answer this particular question. So any doubt in here? So firstly, the protein will undergo unfolding, that is various conformational changes. Then it will form various nuclei, that is nucleation step. And lastly, we have formation of aggregates, that is formation of fibrils, which is known as aggregation. So if any doubt in this question? Okay. So we will move on to our sixth question, which is what kind of surfaces favors protein adsorption? So your options here given as A is hydrophobic surfaces basically. Second option B is hydrophilic surfaces. Option number C is both A and B, that is both hydrophobic as well as hydrophilic surfaces. And D is the none of the above. So you have to say, you have to think about the most appropriate option, that what kind of surfaces favors protein adsorption. Okay, hydrophilic surfaces. So you mean to say that any kind of water repelling surfaces favors protein adsorption, right? Can you just try to think bit more? How can a water repelling surfaces can favor protein adsorption? Sorry, water loving surfaces. Okay, so it's A, you are saying. So yes, the correct answer to this question is option number A, that is hydrophobic surfaces. So how come hydrophobic surfaces favors protein adsorption? So in a particular figure, let me go back to that particular figure. So you can see that any hydrophobic SAM, there will be interaction that lead to fibril formation. Right, in the last it's written, you can in the last figure you can see a hydrophobic SAM, that is hydrophobic self-assembled monolayer. There will be hydrophobic interaction between the hydrophobic core, right, hydrophobic core of the native protein with the hydrophobic surfaces, and this will particularly lead to fibril formation or aggregation. So in the first diagram, you can see that in case of highly hydrophilic surfaces, that in case of water layer, there won't be any fibril formation. Whereas in sorry, in case of hydrophilic SAMs, that is surface as self-assembled monolayers, there will be hydrogen bonding that will accelerate aggregation. However, when there is an hydrophobic interaction, it will be particularly leading to fibril formation. So this also, I think, it was also given in a different slide. Let me go back to it again. So here, so as you can see from here, it was particularly mentioned that hydrophobic surfaces favors the adsorption of protein, whereas hydrophilic surfaces results in very little protein adsorption. So you must remember this, that what kind of surfaces favors the adsorption of protein, right? Okay. So this was the particular answer to this question, that is option number A, that is hydrophobic surfaces favors the protein adsorption and hydrophilic surfaces results in very little protein adsorption. Okay, now we will move on to our next question, which is which among the following is a factor that affects protein aggregation? So I think this is a very straightforward question. So your options here are A, temperature, B, ionic strength, C is solubility, and D is all of the above. Okay, as Amardeep said, D. So correct answer to this question is all of the above. That is all temperature, ionic strength, solubility can lead to protein aggregation. A change in temperature, either a highest on the higher side or on the lower side, can result in the denaturation of the protein, that is from the native stage to the misfolded stage. Even if you change the ionic strength of the particular solution, the protein can aggregate. Again, solubility also affects the protein aggregation. Apart from this, what are the other factors that can affect protein aggregation? Can you name it? Any factor, if you apart from all these three. Yes, pH again, if you decrease the pH or increase the pH, uh, it will affect in the protein aggregation, or it will lead to protein aggregation, right? Also, what else? For example, we have Again, adsorption on surface can lead to protein aggregation. These are particular external factors. Then we have shear, shear as in case of physical, any kind of physical shear. Okay, so this particular question, we have the correct answer is all of the above, that is temperature, ionic strength and solubility. All these three factor affects the protein aggregation. So we have, other than that, pH, solubility, shear, adsorption on surface. Okay, so this question was a very straightforward one. We will move now to the next question. So we have question number 8, which is, which among the following helps in determination of rate of aggregation? So A is Stokes-Einstein equation, B is Boltzmann equation, C is Casey equation, and D is none of the above. So probably in more than 2 questions we already discussed what is this Stokes-Einstein equation and Casey equation is, but we did not discuss what is this Boltzmann equation. However, so can you think that which of the following equation helps in determination of rate of aggregation? So what was that rate of aggregation? So rate of aggregation was basically expressed in terms of K, right? Okay, we will wait for 1 minute and we'll move forward. Again, if you think, try to recall. Okay, Amardeep, you are saying the correct answer is A. So what was this Stokes-Einstein equation for? Uh, so Stokes-Einstein equation was basically DH, right? It determined the DH. DH is your hydrodynamic diameter. So did it consist of this particular term K? Stokes-Einstein equation, did the expression for Stokes-Einstein equation consist of the term K? So as far as I remember, it had Kb. It wasn't K. So Kb was a Boltzmann constant. Then we also had your T, that is your absolute temperature. Other than we had eta, that is the viscosity, and also we had the D. D was your diffusion coefficient, diffusion constant, sorry. So Stokes-Einstein equation was dH is equal to kBT, kBT, that is kB is your Boltzmann constant, T is your absolute temperature in Kelvin, divided by 3 pi eta d. Eta was your viscosity and again D was your diffusion constant. So it did not have that particular rate of aggregation factor A, right? So how can you say that the correct answer is A? So you might have to again rethink about your answer, whether is it A or B or C. Think, you can just think for 1-2 minutes and then we will see what's the correct answer is. So you have been given 4 options. A is Stokes-Einstein equation, B is Boltzmann equation, C is Casey equation, and D is none of the above. So I have already ruled out your one of your option, that is A, that is Stokes-Einstein equation is not the correct one. So I already discussed about it right here. So you may think again, and if you can recall back what is this Boltzmann equation and Casey equation, or even none of the above can be the answer. If none of the above pertaining to all the three equations does not help in determination of the rate of aggregation. So I think Casey equation also, if you recall back the Casey equation, what was it? So Casey equation was cos theta is equal to f1 cos theta 1 plus f2 cos theta 2. So basically when we try to understand this, we felt that it basically gives the relation between the wettability with the factor as chemical heterogeneity. In terms of chemical heterogeneity, how can you take out the wettability or contact angle, that is theta, that is given by Casey equation. So in this particular equation also you don't have the term K, that is rate of aggregation, you don't have. So you can say your option C is also now ruled out. So you have now left with option B and option D. So if you think, what is this Boltzmann equation? Okay, we will now see what's the correct answer to this question is. So I tried to make you understand why we cannot have this A option and C option as the correct ones. But again, we will discuss it with that equation so that it will be easier for you to understand. So the correct answer to this question is your option number B, which is Boltzmann equation, right? So what is this Boltzmann equation? So Boltzmann equation, sigmoidal model, that is IT is equal to I max plus I max minus I naught divided by 1 plus e to the power T naught minus T divided by tau. So here in IT, and what is IT and I max? So I max is your intensity of light at the maximum intensity of light, and IT is your intensity of light at that particular time, and I naught is the initial intensity of light. Oh, sorry, not intensity of light, it is the intensity of the dye, that is the THT dye. And so this particular equation, that is Boltzmann equation, helps you to determine the rate of aggregation. So here also you cannot see where is K, right? You cannot see the term K here. However, if you read it properly, so 1 by tau is the apparent rate constant K. Okay. And lag time is estimated as T naught minus 2 tau. So your rate of aggregation can be determined using this rate constant K, which is the 1 by tau is represented as rate constant. Also Stokes-Einstein equation, see, I already told you it does not have that particular K factor, rather it have KB. So don't get confused between K and KB. So KB here is your Boltzmann constant and not your rate of aggregation. So KB here is your Boltzmann constant, dH is your hydrodynamic diameter, T is your absolute temperature in Kelvin, eta is your viscosity, and D is the diffusion coefficient. So Stokes-Einstein equation basically does not help in determination of rate of aggregation, rather than it helps in the characterization of protein aggregation. So don't get confused between these two. So Stokes-Einstein is the basis for DLS, that is dynamic light scattering, which again helps to determine the hydrodynamic diameter, and it does not help in determination of rate of aggregation, rather than it helps in characterization of protein aggregation. So it actually gives us the particle size, right? Also, you have option C, that is Cassie equation. So Cassie equation, as I already told you, cos theta is equal to F1 cos theta 1 plus F2 cos theta 2. Theta is your contact angle that tells you about the wettability. F1 is the fraction of that particular modified surface. Let's say amine, that is Fa, fraction of amine, cos theta 1. Theta 1 is again the contact angle in case of amine modified surfaces. Again, F2, if you take it as octile, Fo, that is fraction of octile modified surfaces. Cos theta 2 is again, theta 2 is your contact angle of octile modified surfaces. So this particular equation also does not have your K, that is rate of aggregation. So this equation also does not help us to determine the rate of aggregation. So I'll go back to one of the slides wherein we discussed about this determination of rate of aggregation. If you still have confusion between tau and K, how 1 by tau is the apparent rate constant. So I'll move back to that particular slide. So here you can see how you can determine the rate of aggregation using the sigmoidal model of Boltzmann equation. So if you plot a graph between the THT intensity versus time, you will get a sigmoidal curve wherein the like in this particular graph you can see from time 0 to 3 hour it is the lag time, then the slope which you are getting is the growth rate, and lastly you have the stationary phase. So here this Boltzmann equation, particularly IT is equal to I max plus I max minus I naught divided by 1 plus e to the power t naught minus t by tau. Here in 1 by tau is the apparent rate constant k, and lag time can be estimated as t naught minus 2 tau. So if you derive an exponential expression using this particular linear slope that you will get from the growth rate, uh, so you can get this particular expression as it is equal to I max 1 minus e to the power minus kt. So here in it is your intensity of this THT at particular time t is equal to I max, that is the maximum intensity. Then you have minus k, so k is your rate constant or the rate of aggregation, and t is again that particular time. So with a linear slope of it is equal to kt plus c, you can determine the rate of aggregation. So I hope that this is now clear to you. If you have any doubt again in this question, because as you can see, you had option A as Stokes-Einstein equation, B Boltzmann equation, C Cassie equation, and D is none of the above. So Stokes-Einstein equation does not have this rate of aggregation K factor. Again, Cassie equation does not tells you about that. However, the sigmoidal model of this particular Boltzmann equation helps you to determine the rate of aggregation. So I hope this question is clear to you, so that we can move ahead to the question number 9. So any doubts you can ask me here itself. So you all know that this presentation as well as the recorded structure, you can access it from the Swayam portal as well, right? If you don't know, I will be giving you a demonstration at the end of the session. So you may stay back if you want to know from where you can access this particular lecture video as well as the presentation. So it will not just have this particular session's presentation, but all the presentation that has been carried before, like that is week 1, week 2, week 3 and week 4 will also be available there. Okay, I think there is no doubt. So we can just move forward with our next question. So your ninth question is, which among the following instruments helps in analysis of surface morphology after aggregation? So here you have first option is FTIR, that is Fourier transform infrared spectroscopy. Option B is your dynamic light scattering, that is DLS. Option C is atomic force microscopy, AFM. And option D is none of the above. So you have to depict that which of the following instrument help in analysis of surface morphology after aggregation. How can you know the surface morphology after aggregation? Which instrument helps you to determine this particular? Okay, so I've got an answer from Amardeep, that is option number B, dynamic light scattering. So you have to give me the appropriate answer. Just think about a little bit more. Think you are able to understand it, but you're not able to reflect it back. Just think a little bit more. I think you will be able to figure out. Yeah, I'll take the answer as B and again as C. Now you are saying that it's C. We will see if the C is correct or not. So you have to focus on what the question is asking. The question here asks is, which of the instrument help in analysis of surface morphology after aggregation? So does FTR help in analyzing the surface morphology? What does it do? Can you think? FTIR. Again, you have DLS. Can you think that what does DLS helps us to analyze? Then we have AFM, or you can have neither of them as your correct option. Okay, we will try to answer this question. So, as you can see, your first option is FTIR, that is Fourier transform infrared spectroscopy. So, this particular instrument helps you in analyzing the secondary structure of the protein. So, it does not directly tells you about the surface morphology. However, it tells you about this what kind of secondary structure is present in the protein, right? So the peaks, when you get the graph or when you plot it in the Gaussian curves, you will get the peaks which you can compare with the uh, standard peaks, and you can analyze that which of the peaks with that particular wave number is corresponding to what kind of secondary structure, right? So any alpha helix will have that particular wave number. The peak will be present in that particular wave number. Again, for beta sheets, similar situation is there. So FTIR does not help in directly analyzing the surface morphology, rather than it helps in analyzing the secondary structure of the protein. So you can rule out your option number A. So we will next move on to option number B, that is dynamic light scattering, that is DLS. So DLS is used in determining the hydrodynamic diameter, that is the particle size. So does particle size tell you about the surface morphology? Will it tell you about the surface morphology? In particular, it won't. However, it will help you just to determine what's the particle size of that particular protein. So DLS, that is dynamic light scattering, is based on again Stokes-Einstein equation. So wherein you can determine the hydrodynamic diameter of the protein. So option number C is your atomic force microscopy, that is AFM. Now this particular instrument will help you to analyze the surface morphology. So you got the answer as option number C is your correct answer to this question. So surface morphology after or before aggregation can be analyzed using AFM. So there will be a picture from which you can see the before aggregation and after aggregation surface morphology, which you can reproduce from using AFM. Whereas DLS or option number B is for determination of hydrodynamic diameter, and option number A is for changes in the secondary structure of protein, that is FTIR. FTIR is for the changes in the secondary structure of the protein. So I hope you don't get confused between these three instruments. So you may again get questions like which of the following instrument may help you in analyzing the changes in secondary structure of protein. So at that time you have to give the answer as FTIR, whereas you can again get a question which may ask you that which among the following instrument will help you in the determination of hydrodynamic diameter, or say it may again say which of the following can help you in determining the particle size of the protein, right? So in that case you have to give the answer as DLS, that is dynamic light scattering. I hope this is also clear to you. If any doubt is there, you can raise the question here itself. So we will move on to the next question. Just wait a minute. Okay, no doubt. So we will move on to the 10th question. So the question number 10 is, wettability of a surface with chemical heterogeneity is given by option A is Casey equation, option B is Boltzmann equation, option C is again Stokes-Einstein equation, and option D is Wenzel equation. Okay, so I've got the answer as option number A. So I'll let other people also to absorb the question, and then I'll try to, because few of the students have joined later in the session, so I may also discuss every equation with them as well. Fine, so it's nice that I'm getting the answer. So you can see if you solve just this kind of question only, you will be able to solve other questions as well. So it makes very easier if you go through the lectures just for even 2 hours recap, then you will be easily able to answer the question as I can see now. So option number A, Casey equation, option B, Boltzmann equation, option C, Stokes-Einstein equation, and option D, Wenzel equation. So for other people apart from Amardeep, if you can recall back every equation and think if that particular equation gives you the relation between the wettability of the surface with chemical heterogeneity or not. So you are able to understand the questions properly. This question is asking you that The wettability of a surface with chemical heterogeneity is given by which of the particular equation? How can you analyze the wettability of a surface in regards of chemical heterogeneity? So again, a question can be asked here that wettability of a surface with physical heterogeneity is given by which of the equation? Can you tell me that which among the following can again give the wettability of a surface in with regards to physical heterogeneity and not chemical? Can you tell me? Okay, we will try to solve this question first and then I'll also try to answer to the other question again. Right. So the correct answer to this particular question is your option number A, as Amardeep said, is Casey equation. Okay. Okay. Fine. Then D will be the answer. Yes. So we'll see what basically is all of this equation. So your option number A, that is the Casey equation, cos theta is equal to F1 cos theta 1 plus F2 cos theta 2. So F1 and F2 here are giving your chemical heterogeneity. So any fraction of amine or other kind of modified surfaces are given by this F1 and F2. So Casey equation pertains to your wettability of the surface with chemical heterogeneity. Okay. So wettability is your contact angle, that is theta here. So theta is the overall wettability, whereas theta 1 is pertaining to like first number 1 modified surface and theta 2 may be the number 2 modified surface. Next you have Boltzmann equation. Again we studied that Boltzmann equation, we use it for determination of rate of aggregation. So what was the equation? It was IT is equal to I max 1 minus e to the power minus kt, right? So in this particular equation also, it does not talks about the contact angle and hence you can rule out this option. Basically, it is used for determination of rate of aggregation. Option number C you have is Stokes-Einstein equation. So again, Stokes-Einstein equation which we already discussed in few of the previous questions. It is the basis for dynamic light scattering and the equation is given as dH is equal to, if you want me to write it here I can write it down, but also it is available in other slides as well. So dH is equal to kBT. Kb is your Boltzmann constant, T is the absolute temperature in Kelvin, then divided by 3 pi eta d. So eta is the viscosity and d is the diffusion coefficient. So this particular equation also does not talk about the wettability. That is, you cannot find any theta in this equation. So you are left with option number D, that is Wenzel equation. So Wenzel equation is basically cos theta is equal to Rf cos theta naught. Now this Rf is your roughness factor, right? So if you get any question wherein you are asked that wettability of a surface with physical heterogeneity is given by, so physical heterogeneity is given by this Rf, that is roughness factor. So in that case you have to answer the question as the Wenzel equation. So in that instance Wenzel equation will be the correct option, right? I may just write it here. So if this is particularly asked, so Rf is your roughness factor and this is wettability of a surface with physical heterogeneity. And this one also you must remember. So I have wrote it down so that you don't forget it. Fine. Is there any doubt in this particular question? So if there is no doubt, we can move ahead. So we may move ahead to the 11th question. So you have your 11th question as, which of the following act as a therapeutic solution for protein aggregation? So you have to tell me, you have to depict which of the following does not allow protein aggregation. So it is a solution for protein aggregation, which is basically to avoid protein aggregation. So herein you have options as A is inhibition of aggregation, B interference with post-translation peptide changes, C aggregate clearing mechanism, and D is all of the above. So I have already got the answer from Amardeep, as he says the answer is D, that is all of the above. Okay, we will try to see why it is D. Let other people also absorb the question. So which of the following help us to avoid protein aggregation? That is, which of the following act as a therapeutic solution for protein aggregation? Inhibition of aggregation, interference with post-translation peptide changes, aggregate clearing mechanism, and D is all of the above. So I already got the answer from Amardeep, as he said the answer is D. So we will see which is he correct or not. So yes, the correct answer to this particular question is option number D, that is all of the above. So why so? So you have to think that which among the following act can help us in avoiding the protein aggregation. How can you avoid protein aggregation? So either you can inhibit the protein aggregation in any form, like if you add any kind of external factors, you can inhibit the protein aggregation. Second is interference with post-translational peptide changes. Okay, so so I lost my network in between, so I'll try to repeat it again. So what kind of therapeutic solutions you can use to avoid protein aggregation? So first is inhibition of protein aggregation. So you can inhibit the protein aggregation process using any kind of external factors. Second is interference with post-translation peptide changes. So any post-translation peptide changes, if you add on before the misfolding step or before the aggregation step, you can avoid the protein aggregation. And lastly, if your aggregate has been already formed, how can you avoid those particular situation? So in that case, you can again go for upregulation of molecular chaperones. So these particular molecular chaperones help in converting the misfolded protein again back to the native state, right? So they help in restoring back the functionality of the protein. So any aggregate that has been formed or any misfolded protein structure which has been formed can be again converted back to the native state using these kind of molecular chaperones, basically upregulating it. And lastly, we have aggregate clearing mechanism. So various again aggregate clearing mechanisms are involved, wherein you can clear back the aggregate that is formed. So the correct answer was option number D, that is all of the above. Right? So is there any doubt in this question? We are left with one more question and we are reaching towards the end of the session. If you have any question, you can raise it here as of now. Okay, so the last question we have is question number 12, which is which of the following events does not occur during lag phase of protein aggregation. So you have to tell me which of the following events does not occur. So you have to look at the question very clearly. It is asking which of the events does not occur during lag phase of protein aggregation. So you have been given the options: A, conformational change; B, adsorption; C is precipitation; and D is all of the above. So you have to again think back what were the events, or what is the sequence of the events in case of protein aggregation, and what kind of events occur specifically during the lag phase. So you know, right, what is the lag phase? So when you plot a graph between the THT intensity versus the time, you get a S, or the sigmoidal shape curve, right? So at the bottom, which is the initial phase, is termed as the lag phase, and the linear slope is your growth phase, whereas the ending phase is the stationary one. So can you tell me which of the events does not occur during lag phase of protein aggregation? Okay. So Amardeep says that the answer is C, that is precipitation. Fine, you are totally correct. So during the lag phase, we usually have conformational changes occurring due to external factors or due to the adsorption of the protein on the surface. Your option A is ruled out. So it occurs during lag phase of protein aggregation. Option B you have is adsorption. So again, adsorption is the first or the primary step due to which we have this conformational change, right? Option C is precipitation. So we do not have precipitation during protein aggregation. So your correct answer is option number C, which is precipitation. So this particular event does not occur during lag phase of protein aggregation. So from the figure, as you can see, so the lag time, we have adsorption, conformational changes, again we have nucleation. So for this particular question, if the option number D, if it might have been nucleation, so do not get confused whether precipitation or nucleation will be the correct answer, right? So you must remember that during the lag phase of the protein aggregation, you have adsorption, you have various conformational changes, or even if unfolding is there as an option, unfolding is also a correct option. Correct option as in it occurs during the lag time. Then you have multi-layer adsorption. So instead of adsorption, it can be also written as multi-layer adsorption. So don't get confused between multi-layer adsorption as well, between adsorption and multi-layer adsorption. So multi-layer adsorption is basically formation of nuclei or nucleation. And lastly, we have formation of aggregates, that is fibrils at the surface. So apart from the last step, all the other three steps are being seen in the lag phase. I hope this particular question you are being able to understand. So before concluding the session, I would like to show you from where you can access these particular slides. So these particular slides, as well as the YouTube video link also you can get for this particular session. So if you go to the Swayam portal and log in with your ID, I'll stop presenting this one. I'll share with you another tab. So you can see from this, can you, yes. So this is the particular portal from which you access your course, right? And all the course outline as well as the assignments have been given in the left side of the screen. Can you see that course outline. So at the end of that column, you will get this particular, at the last ending, you will get this particular option, that is problem solving session. And if you click on this particular problem solving session, you will again get two various option. One is problem solving session and another is survey on problem solving session. So survey is the feedback, you can give it from there. Other than that, if you click on the first tab, that is the problem solving session, so you will be redirected and you will be taken to another tab, that is another window. Wait. So this will be the particular window that you can see when you click here. So from here you can access all the particular week 1, week 2, week 3, week 4 till week 8 YouTube links as well as the presentation folder links. Right, so if you haven't uh, joined any of the earlier session, you can again refer back to these sessions if you want to. So that's all I wanted to say. If there is any problem uh, or any doubt regarding the course, you can go to the discussion forum and ask a question there. So now we will conclude this session. We will conclude our session number 5. So thank you everyone for joining this particular session. So you can leave. Thank you.